Bristol, Rhode Island. 1962. A factory floor the size of a football field. Workers in goggles and rubber gloves are laying sheets of woven fiberglass cloth into an open mold, soaking each layer by hand with polyester resin that costs $2 a gallon. Oil is $15 a barrel. Nobody is doing the math on how thin this hull needs to be because nobody has to. The resin is cheap, the cloth is cheap, and every engineering problem has the same answer: add another layer. These boats will still be sailing 60 years later. The ones being built today will not. Fiberglass did not win the boat building industry because it was the best material for crossing an ocean. It won because it was the best material for running a factory. And the difference between those two things has been costing boat owners money for 6 decades. Have you ever looked at what your boat is actually made of and asked why? Tell me in the comments what hull material you trust most. This is Yachts and Boats. Subscribe so you catch the next one. In 1942, a boat builder named Ray Green in Toledo, Ohio, built the first fiberglass hull. It was an experiment. The material was brand new. Owens Corning supplied the glass fabric. American Cyanamid supplied the resin. By the late 1950s, fiberglass had overtaken wood for production boats. Pearson Yachts in Rhode Island, Morgan Yachts in St. Petersburg, Cal and Columbia, and Islander on the West Coast in Costa Mesa, California. These builders took fiberglass and turned it into an assembly line material. One female mold, one hull shape, hundreds of copies. The boats from the 1960s used hand layups. Workers placed alternating layers of 24-ounce woven roving and 1.5-ounce mat by hand. They rolled out the air bubbles with serrated rollers. There were no chopper guns, no shortcuts, no pressure to go fast, and because resin cost $2 a gallon, every hull came out thick. That thickness was not a design choice. It was the result of not knowing how thin they could go without the boat breaking. Practical Sailor documented this. Builders solved engineering challenges by adding material, not engineering precision. The Pearson Triton, designed by Carl Alberg in 1958, sold for $9,700. Over 700 were built. Solid fiberglass hull, long keel, full encapsulated ballast. Many of them are still sailing. The Alberg 30, introduced in 1962, followed the same formula. Over 700 were built in Canada by Whitby Boat Works. Solid fiberglass, long keel, iron ballast encapsulated inside the layup. These boats were not fast. They were not light. They were built by people who did not trust the material enough to use less of it. That distrust produced the most durable recreational sailboat hulls ever manufactured. Chris Craft built its first fiberglass cruiser in 1964. The 38-foot Commander was molded in 3 hull pieces because the factory ceiling was too low to build it in one. The seams forced the builders to compensate with extreme overbuilding. The result was a hull so thick it would stop a large caliber bullet at point-blank range, according to period documentation. Commander owners today would not trade them for a newer, lighter boat. The weight that slowed them down is the same weight that kept them intact for 60 years. The legendary naval architect L. Francis Harrishoff called fiberglass frozen snot. He hated it. He lost that argument because no wooden boatyard on Earth could compete with a factory that stamped out hulls like cookie cutters. By the end of the 1960s, the underground sales slogan for the material was reportedly, "Wrap your ass in fiberglass." The pattern is not accidental. Fiberglass won on production speed. The builders who adopted it first built hundreds of boats per year. Every one of those builders is now defunct. Pearson, Morgan, Columbia, Cal, Islander, all gone. The boats survived. The companies that built them did not. And then the industry discovered something that changed the math permanently. They discovered they could go thinner. By the 1970s and the 1980s, oil prices climbed. Resin prices followed. Builders found they could reduce hull thickness without the boat failing immediately. The chopper gun replaced the hand layup. Production got faster. Hulls got lighter. Buyers wanted speed and interior space. Builders wanted margin. The earliest fiberglass hulls were solid laminate throughout. No core, no filler. Just glass and resin, layer after layer, until the builder felt confident. Modern production fiberglass sailboats use cord construction. That means two thin fiberglass skins bonded to a core of balsa wood or closed-cell foam. The core creates a structural sandwich that is stiffer per pound than solid laminate. It saves weight, it saves resin, it saves the builder money on every hull. A 40-foot production sailboat in 2026 uses a fraction of the material that a 1960s Pearson or Morgan used on the same size hull. The buyer pays more, the builder spends less. That gap is margin. And cord construction introduces a failure mode the 1960s boats never had. When water intrudes through a deck fitting, a chain plate, or a through hull into a cord hull, the core absorbs it. Balsa rots. Foam delaminates. The structural sandwich separates from the inside. The hull feels solid on the surface while the core turns to mush behind it. 1 in 4 fiberglass boats develops osmotic blistering, according to Bilboes Marine. Water pushes through the gel coat, reacts with chemicals in the laminate, and forms acidic pockets that blister the hull from below. Marine surveyor David Pascoe examined roughly 4,000 hulls over 30 years. Fewer than 10 had serious structural damage from blistering. Most blistering is cosmetic. The repair is not cosmetic. Full osmotic remediation on a 35 to 40-foot sailboat runs $15,000 to $30,000. The yard strips the gel coat, blasts the surface, dries the hull for weeks, rebuilds it with epoxy, applies barrier coat, and repaints. The yard dries the hull for weeks, sometimes months. Moisture meters dictate the schedule. You pay storage the entire time. That bill does not exist on a steel hull. Steel does not blister. It does not delaminate. It does not absorb water into a hidden core. That bill does not exist on an aluminum hull. Aluminum forms a protective oxide layer on contact with air, and it does not exist on a cold molded wood and epoxy hull. The epoxy encapsulation seals the laminate from water intrusion entirely. The material the industry chose for mass production is the only common hull material that develops a chronic, progressive, water-driven disease after years of immersion. The math is not subtle. Fiberglass created a second problem the industry has no answer for. Every year, more than 100,000 fiberglass boats in Europe reach end of life. The Floating Stories Lab reported in 2025 that only about 2,000 are recycled. 6,000 to 9,000 are abandoned. The rest go to landfill. Fiberglass does not rot. It does not corrode. It does not break down. It sits in the ground for centuries. Holland and Germany have already banned fiberglass disposal in landfills. Boat Breakers reported this in February 2026. The United States has no equivalent ban, no national recycling program, no plan. Europe expects 140,000 composite boats per year to become due for scrapping, based on 6 million recreational craft with 30 to 45-year lifespans, according to Boat Breakers. Now look at the United States. There are 12 million registered recreational boats. According to Mordor Intelligence, 65% of them have fiberglass hulls. That is roughly 7.8 million fiberglass boats with no viable end-of-life pathway. Millions of those were mass-produced in the 1970s and the 1980s. They are all reaching end of life at the same time. A steel boat at end of life has positive scrap value. You call the scrapyard. They come to you. They cut it up. They pay you by the ton. An aluminum boat works the same way. Aluminum scrap has high market value. The yard wants it. A wooden boat biodegrades. It was designed to return to the earth. A fiberglass boat has negative value. You pay to get rid of it. The landfill charges by the ton to accept it. The hauler charges to transport it. If you abandon it, the state charges the taxpayer to remove it. That single fact changes every ownership calculation the industry never shows you at the boat show. The number nobody quotes is the one that matters most, which costs more over a lifetime. The boat you bought or the boat you throw away? France built a national boat recycling program through APE, funded by a levy on every new boat sale. The US has done nothing comparable. Rhode Island ran a pilot program that shredded derelict fiberglass hulls and shipped the fragments to a cement manufacturer in South Carolina. That is the state of the art. grinding boats into cement filler. Meanwhile, Florida removed 475 derelict vessels from its waterways in 2025 alone. The taxpayer covered the cost. The Dutch non-profit Stichting Yacht Recycling was created specifically to solve this problem. Their findings were blunt. At most, 10 to 20% of an average fiberglass boat can be turned back into raw materials. The rest goes to landfill or gets burned. The International Maritime Organization commissioned a study on end-of-life boat disposal in 2016 with a focus on small island developing states that have no landfill capacity at all. A decade later, no scalable solution exists. The boating industry generates $230 billion in annual economic impact in the United States, according to the NMMA. It supports 812,000 jobs. It sells 95% of its boats domestically, and it has no plan for what happens when those boats stop floating. Every fiberglass boat sold today carries a future disposal cost that nobody quotes at the point of sale. The buyer inherits it, or the buyer's estate does, or the marina does, or the taxpayer does. The ledger does not lie. Now consider the material the industry passed over. Steel has been used to build ocean-going vessels for more than 150 years. It is not exotic, it is not experimental, it has the longest proven track record of any hull material afloat. In 1970, Che Blythe sailed a 59-foot steel ketch named British Steel the wrong way around the world, east to west, against prevailing winds and currents, solo, in 292 days. Topper Hermanson, a custom boat builder in Fernandina Beach, Florida, circumnavigated in a 26-foot wooden folk boat from 1968 to 1976. While cruising New Zealand and Australia, he watched steel boats survive repeated groundings that would have destroyed fiberglass hulls. The owners sat back and waited for the tide. Hermanson came home and built his next boat in steel. In Australia and New Zealand, steel sailboats in the 40 to 50-foot range are common. Attainable Adventure Cruising reported in January 2025 that properly finished steel boats are routinely mistaken for fiberglass in Antipodean marinas. Nobody considers steel unusual down there. The reason is simple, and it comes down to one word: ductility. Steel bends, fiberglass cracks. When a steel hull hits a reef, a container, or a rock shelf at 3 in the morning, it dents. The water stays out. The boat stays afloat. A fiberglass hull in the same collision fractures. The laminate separates. The ocean comes in. A properly maintained steel hull lasts over 50 years. North Pacific Yachts confirmed this in February 2026. Steel is repairable anywhere in the world with a welder, a grinder, and a can of primer. A fiberglass repair in a remote anchorage requires specialized epoxy resin, biaxial glass cloth, controlled temperature, dry conditions, and someone who knows the layup schedule. Miss any one of those and the repair fails. The cruiser anchored in Tonga with a dented steel hull and a MIG welder aboard is self-sufficient. The cruiser anchored in Tonga with a cracked fiberglass hull is calling for a salvage tow. The difference is not skill. The difference is material. One material keeps you sovereign. The other makes every hull failure a supply chain problem. Aluminum takes the steel argument and removes the weight penalty. It is roughly 60% lighter than steel at equivalent strength. French builders, Ovni, Allures, and Garcia have built expedition-grade aluminum blue water cruisers for decades. When left unpainted, aluminum forms a protective oxide layer and never needs recoating. Cold-molded wood and epoxy offers another path. Brooklyn Boatyard in Maine has built 60 cold-molded boats since 1990. According to soundings, every single one is still floating. 33 years, 100% survival. Cold-molded hulls sealed in epoxy are immune to osmotic blistering because the encapsulation prevents water from reaching the laminate. Yachting World reported in 2023 that cold-molded wood and epoxy hulls require no more maintenance than fiberglass. The construction method laminates multiple layers of wood veneer at opposing angles over a mold, bonded with epoxy and often sheathed in fiberglass on the exterior for abrasion resistance. The result is a monocoque shell that is lighter than steel, stronger per pound than solid fiberglass, and immune to the chronic water intrusion that plagues production GRP boats. Material cost tells part of the story. Steel runs $8 to $15 per square foot. Fiberglass runs $5 to $15 per square foot. Aluminum runs $10 to $20 per square foot. Wood runs $2 to $10 per square foot. Yacht trading. Published these ranges in February 2025. The raw numbers look close. The lifetime numbers do not. The alternatives exist. They have always existed. The reason 65% of the recreational fleet is fiberglass has nothing to do with what is best for the person who sails the boat. It has everything to do with what is cheapest for the company that builds it. Resin prices surged between 2023 and 2026. Mordor Intelligence reported that fiberglass and resin cost increases compressed OEM gross margins by 3 to 5% during that period. The industry's response was not to build in a more durable material. It was to thin the laminate further and pass the cost forward. The only monopoly they can enforce is the one you accept. The boat show does not display the disposal bill. The listing does not mention the scrap value. The broker does not compare the repair cost of a fiberglass hull to a steel one at a boatyard in Fiji versus a welding shop in Tonga. The industry chose a material that is cheap to mold, fast to produce, and impossible to recycle. Steel, aluminum, and cold molded wood chose differently. The 60-year-old hull design is not a step backward. It is the step the factory skipped to protect its margin. If this is the kind of story you want more of, subscribe to Yachts and Boats.